Okay, okay then. Hello everyone. Welcome to a new session of our geometry webinar, AmSurAmSul. It's a pleasure to have you all here again. And then today our speaker will be Raquel Villacampa from Centro Universitario de la Defensa de Zaragoza en España. And she will speak about nilmanifolds, examples and counterexamples in geometry and topology. Okay, thank you, Raquel.
Thank you very much, Adrian. Thank you very much for all the organizers for giving me the opportunity to speak in this seminar. First of all, I would like to apologize because I don't know why, but I thought that this webinar will be in Spanish. So my slides are written in Spanish. I'm going to speak in a mixture between Spanish and English, and I hope that it is not a problem that the slides are in Spanish. In any case, you can ask if something is not clear or something. Okay, so the outline of the talk is the following. I will start by giving a brief introduction to complex manifolds and Hermitian structures. And then I will move to complex nilmanifolds. And then we will divide the study into two parts. One part is for the lower dimensions, that means dimensions 4 and 6. And the last part is devoted to dimension 8. All the things that I'm going to explain is a summary of results with many collaborators that appears in the slide in alphabetical order. So, okay, the setting for all the talk is complex geometry. So we will work with complex manifolds. I'm going to construct them and to study some properties that can be of metric type or cohomological type. A complex manifold is formally is like a differentiable manifold, but now the change of charts, this composition of charts, must be holomorphic. So if we have a complex manifold of complex dimension M, then the underlying manifold is a differentiable manifold of a real dimension 2. We can ask when the opposite is satisfied. So for that, we need almost complex structure that is an endomorphism of the space of vector fields such that its squares is minus the identity and satisfying the Newlander and Nirenberg theorem. That is, if we have almost complex manifold, then it is complex if and only if the Nijenhuis tensor vanish identically, where the Nijenhuis tensor is given by this expression here. Well, two different complex structures over the same differentiable manifold can produce different complex manifolds. So we can have different structures over the same differentiable manifold, but on the complex point of view, the complex manifolds could be the same manifold or could be different manifolds. So we will see in our context these situations. Well, we will work with Hermitian structures on complex or on almost complex structure. So Hermitian structure is a pair JG, where J is a complex structure and J is a Riemannian metric, such that the complex structure defines an isometry on the space of vector fields. When we have a Hermitian structure, it is always defined the fundamental 2 form that is defined as appear in the screen. And properties on the fundamental 2 form defines different types of geometry. So the more special type of geometry is Kähler geometry, which appears when the 2 fundamental form is closed. This condition is very strong, and it imposes several restrictions over the manifold. For instance, if we have a Kähler structure, then the manifold is complex and it is symplectic. Moreover, there are other topological restrictions over the manifold. For instance, the even Betti numbers are different from 0, and the odd Betti numbers are all even. Also, the Didi-bar lemma is satisfied, and the Fröhlicher spectral sequence degenerates at the first step. So, as I have said, Kähler structures imposes very restrictive conditions on the manifold, and it is difficult to find examples of Kähler manifolds in the literature. So what we can do is weaken this Kähler condition. When we weaken this condition, then new Hermitian geometries appear. So which are these new geometries that appear when we weaken the Kähler condition? Okay, let us see. For instance, we have these 3 geometries. Define balance condition, which is this one. These one are balanced. In this case, the power n-1 of the fundamental 2 form is closed. This condition obviously is this condition weaken the Kähler condition 1. Another way to weaken the condition is to define the strongly Gudusson condition. In this case, power n-1 of the fundamental form satisfy the condition that the partial of this form is D-bar exact. And it can be generalized by the Gudusson condition. Another way, in order to weaken the Kähler condition, is in this other way around, for which we have the pluriclosed forms, for which Didi-bar of the fundamental form is closed, and this can be generalized by the first Gudusson condition. Another definition is the Asteno-Kähler matrix, for which the power n-2 of the differential form is Didi-bar closed, and similar to the first Gudusson condition, we obtain the n-2 Gudusson condition. Okay, first Gudusson condition, in this way, we obtain also the 2 Gudusson condition, the 3 Gudusson condition, and so on, the n-2 Gudusson. But there is no implications one to each other condition. Well, there are several properties among all of these conditions. So, first of all, Gudusson in the 80s proved that any compact complex manifold admits a Gudusson metric. Of course, Gudusson does not define Gudusson metrics. he called these metrics as standard, but now we know them as Gaussian. So this class this class is like nothing, because any compact complex manifold admits this kind of metrics. On the other way, observe that SKT metrics and Steno-Kähler coincide if n equal to 3, because n minus 2 is equal to 1, and we obtain the SKT condition. So, in order to obtain new K Gaussian conditions, we need manifolds with complex dimension greater of or equal than 4. So in this map of Hermitian geometry, this depends on the dimension of the manifold. Okay. I'm going to focus my attention on nilmanifolds. A nilmanifolds is a compact quotient. G is a Lie group that is simply connected, and nilpotent, and gamma is a discrete subgroup of maximal rank that can be named as lattice. As an example, we can think of this. We consider the set of matrices that are upper triangular matrices with 1 in the main diagonal. This is called the Heisenberg group of dimension 3. Well, this group is in fact a Lie group where the Lie bracket is given by the commutator of matrices. This group is connected and simply connected since this group of matrices is diffeomorphic to R3. In fact, any matrix can be identified with the tuple A, B, C. So we have the diffeomorphism with R3 in a natural way. And this Lie group is nilpotent since the Lie algebra associated to this Lie group is nilpotent. So, okay, if we consider the matrices whose entries are integer numbers, and we make the quotient, we obtain a nilmanifold. This nilmanifold is very important because Thurston in 1976 used it in order to construct the first example of manifold that is symplectic and complex, but it is not Kähler. The example is this Heisenberg group multiplied by S1, because we need a manifold of even dimension. Okay, so we obtain the first use for nilmanifolds in order to obtain the first example of a manifold that is complex and symplectic but not Kähler. In fact, this result is not a surprise some years after, because in the 80s, late 80s, Benson and Gordon and then Hasegawa proved that in fact a nilmanifold is Kähler if and only if it is diffeomorphic to a complex torus. In this setting, observe that nilmanifolds are a good class of complex compact manifolds in order to study Hermitian geometry, but non-Kähler Hermitian geometry. So, study this type of manifolds, we are going to obtain examples of manifolds satisfying certain properties, and we are sure that these manifolds are non-Kähler. Okay. So we focus on nilmanifolds, and we are working with invariant Hermitian structures. These structures comes from structures living on the Lie algebra associated to this Nilmanifold. And what are the adventures to work with invariant complex structures? Okay, first of all, we work at the Lie algebra level. This is very important because we can work with tools of linear algebra of finite dimension. So in this way, things are much more easier than the usual tools of differential geometry. Moreover, we are working at the Lie algebra level, but in some cases we obtain results on the whole manifold, thanks to a process called symmetrization. This process means that when this process applies, that are in many cases, if we obtain the existence of a Hermitian structure on the global at the level of the Nilmanifolds, then it exists a structure of the same type, but at the level of the Lie algebra. That means that if we study the existence of properties or structures at the Lie algebra level, and we prove that this particular structure does not exist at the Lie algebra level, we can conclude that this particular structure does not exist on the Nilmanifold. So this way of work is really important for these manifolds. Also, this result of Nomizu is very important and is the following. It says that the the RAM cohomology of the Nilmanifold can be computed at the Lie algebra level because it is isomorphic to the Chevalley-Eilenberg cohomology of the Lie algebra. Moreover, there are similar results of this Nomizu theorem for other cohomologies, complex cohomologies, for instance, for the Dolbeault cohomology, for the Fröhlicher spectral sequence, for the Botchen cohomology, and so on. There are many results relating the cohomologies of the Nilmanifolds related to the cohomology of the Lie algebra. And finally, we can assure the existence of lattices just simply observing the structure equation of the Lie algebra. In fact, if the structure equation of the Lie algebra has rational coefficients, then by Malchev theorem there exist lattices, and therefore it is possible to construct Nilmanifolds associated to this Lie algebra. So I hope that I convince you that working with Nilmanifolds is a nice context in order to first to work in a simple way, and then let us see that it is nice to obtain good results in non-Kähler geometry. Well, so we focus our attention on nilpotent Lie algebra. And let us define what is a complex structure on a nilpotent Lie algebra. For that, we define they are endomorphisms of the Lie algebra such that its squares is minus the identity and satisfy the Nijenhuis condition. Okay, this complex structure can pass through the dual. I mean, we define this complex structure defined on forms in this way here, And now we can complexify the Lie algebra. In this case, the complexification of the Lie algebra splits into two summands. One of them is the fundamental subspace associated to the two eigenspaces, eigenvalues I and minus I, which are the eigenvalues of the complex J. Okay, now the Nijenhuis condition is equivalent to say that the differential of 1-0 forms also is a two form that can be expressed in the 2-0 part and the 1-1 part. And the 0-2 part vanishes identically. Here we have two special types of complex structures. So if the differential of a 1-0 form is of 2-0 type, then the complex structure is set as complex parallelizable. And if the differential of a 1-0 form is of type 1-1, then the complex structure is said to be abelian. So, okay, this is our context, and now we can ask several questions. So, for instance, which nilpotent Lie algebras admits complex structure? And if we have one of these nilpotent Lie algebras admitting complex structure, how many complex structures admits this nilpotent Lie algebra? Okay, let us start by the smallest dimension. So what happened in dimension 4? Okay, for dimension 4, there exists only 3 nilpotent Lie algebras being non-isomorphic, but only 2 of them admits complex structure. And moreover, there is only exists one complex structure for each Lie algebra. And all this situation is codified in these complex structures here. The two manifolds, or the two nilpotent Lie algebras admitting complex structures are the torus and the Kodaira-Thurston manifold, and both of them can be codified here in the complex structures, where epsilon, if epsilon is equal to 0, we obtain the torus, and when epsilon is equal to 1, we obtain the Kodaira-Thurston manifold. In dimension 6, we have more manifolds. In fact, we have 30-fold nilpotent Lie algebras, but only 18 of them admit complex structures. The list of them is this one here, and it is due to Salomon. Sorry. And the list is given here in the screen. So an nilpotent Lie algebra of dimension 6 admits a complex structure if and only if it belongs to this list. Here, the notation is the following. For instance, in H5, we have this 6 tuple, which means the following. There exists a basis A1 to A6 such that the first two elements are closed, and now the fifth element, the differential of the fifth element, is just the product of the first and the third and the fourth and the second. Okay, this is 13 plus 42, and a similar thing for the other, 14 plus 23. Okay, so these are the 18 complex structures. The number of complex structures in each of these Lie algebras, it depends on the Lie algebra. So, for instance, this is the classification of all the complex structures in dimension 6. observe that it appears for families. These families depending on different different topological aspects. But for instance, this one here appears the complex parallelizable structures. Here, for instance, if rho equals 0, we obtain a billion complex structures. So here we obtain a rich variety of cases. Well, in fact, in this paper with Ceballos, Otal, and Ugarte, we specify exactly for which value of the parameters lambda, d, b, c we live in one in the Lie algebras in the list of Thurston. So, for instance, focusing only in abelian complex structure, we obtain this classification here. So, for instance, I want to focus on H4. Observe that here, for instance, we obtain one abelian structure and infinite non-isomorphic non-abelian complex structures, all of them depending on a real parameter. Okay. After that, we can study the Hermitian metrics over these structures. So recall the weaken of the Kähler condition, and we study this balance condition and the strongly Gudosian condition in this family. We obtain the following. In the case of non-abelian complex structures, all of the structures admits a strongly Gudosian matrix. But not only admits balance metric, only these ones put here in red color. In the case of abelian structures, it is equivalent for a complex structure to admit balance and a strongly Gudosian metric. So observe this condition, this algebra here, H4. Recall that this algebra has only one abelian structure here, okay, and the infinite family of non-abelian complex structures. But now this abelian structure does not admit any strongly Gudosian, neither balance metric, and in the non-abelian case, not all the structures admit this particular matrix, only this with this particular choice of the parameter. Okay. So this is our study in dimension 6. Okay, this is the thing that I want to observe. Okay, so the title of the talk was examples and counterexamples given by Nilmanifolds in topology and geometry. So. Up to the moment, I have explained that in complex dimension 2, the Kodaira Thurston Nilmanifold is the first example of complex and symplectic manifold that is non-Kähler. Okay. In dimension 6, we have done a complete study of Nilmanifolds in this dimension, and I want to show 2 applications of this study. The first one is the stability of properties under the formation of the complex structure, and the second application is the study of the holonomy of a specific connection and the relation with some special Hermitian geometry. So, okay, let us see this first application of deformation properties. So let us consider an open neighborhood of number 0 in the complex numbers. So a property P of a compact complex manifold is called open or closed under holomorphic deformation if the following sentences apply. So consider a family of compact holomorphic manifolds that are codified by a number A belonging to this neighborhood nabla. Okay, so if we have a property that holds for a specific complex manifold, if this property can be generalized for the complex structures in the neighborhood, then the property is called open. Okay. On the other way around, if a property holds for all the complex structures in a disk except for one, and then for this particular point the property holds, then the property is called closed. Okay, so now we are going to consider two properties. The first property is the existence of a balance metric. Then in the 90s, Alessandrini and Bassanelli proved that this property is not open. And many years later, Popovici conjectured that this property is closed. In a similar way, Popovici proved that the existence of strongly Gaussian metrics is open and conjecture that it is closed. Okay, so we have a complete study of Hermitian metrics on Nilmanifolds of dimension 6. And with this study, we can prove that these two conjectures fail. And in fact, we prove that these two properties are not closed. And the proof is the following. If we remember this H4 that we are explaining some minutes before, this is the counterexample to these conjectures. So there exists a family of complex manifolds such that the central element of the family does not admit any strongly Gaussian metric, and of course neither any balance metric, but all the complex manifolds in this neighborhood has balance and strongly Gaussian metrics. And as I have said, this example lives in a manifold whose underlying Lie algebra is H4. In order to prove that, we use the following. Consider the abelian complex structure on H4. If you remember, is in the left column that I have explained before, the only complex structure that lives here. And well, this complex structure is deformed. There exists a family of deformations that are called the Kuranishi deformations of this complex structure that were studied by these authors, but McCaulin, Peterson, Poon, and Salomon. All the deformation of this complex structure are codified in these equations here, where the unknowns are these big phi functions. So we have fixed some values for this phi function, and obtain these complex structures depending on the parameter A. Okay, this is a family of complex structures. Observe that when A is equal to 0, we obtain a structure J0. And as we have said before, this is the abelian complex structure in H4. And in this case, we have any strongly Gaussian metrics. Well, when A is different from 0, this expression here, a family of complex structures. Okay, we have a dictionary of complex structures on any nilpotent algebra. And this particular complex structure does not belong to our dictionary. But, we obtain different classes of equivalence, and now we have to obtain which is the class for which this structure belongs. Okay, so we make here some computations in order to obtain the class for which it belongs, and we obtain that all these complex structures are equivalent to these structures here. This structure here belongs to our dictionary, and here the main point in order to identify the structures is this coefficient D. So recall the slides before where we have obtained that this type of structures admit balance metric if and only if this parameter D is less than 1/4. So, okay, since A is a complex number whose modulo is less than 1, this parameter is always less than 1/4, and therefore all of these complex structures admit a balance metric. So, putting all things together, we obtain that the existence of a balance metric and the strongly Gaussian metric is not a closed property, because we have a family of complex structures such that here there exists balance metric, but here not. Here it does not exist. So this is a counterexample to the conjectures. Okay, a second application is related to the holonomy of a certain linear connection. Okay, so let us see quickly the definition of the holonomy group of a linear connection. So let us consider a simply connected manifold and a linear connection over the manifold. Let us fix a point P over the manifold, and gamma be a closed path based on this point P. Then the parallel transport along gamma defines an endomorphism of the tangent space of the manifold based at the point P. So these endomorphisms can be composed, and with this composition, they define a group. And this group is called the holonomy group of the linear connection based at the point P. Since the manifold is simply connected, given 2 points, there exists a path joining these 2 points. So the holonomy group at the point P is conjugated to the holonomy group at the point Q, and therefore we can remove the point of the definition and just speak about the holonomy group of the linear connection. Okay. The canonical linear connection is the Levi-Civita connection. So we can ask which are the groups, the holonomy groups of the linear connection. So in general, the holonomy group of the Levi-Civita connection is a subgroup of the orthogonal group or of the special orthogonal group in the case that M is orientable. But Berger, in the 50s, classified all the possible groups, that are that can be realized as holonomic groups for the Levi-Civita connection, and the possibilities are the following. So if we consider a simply connected manifold that is also reducible and non-symmetric, then the possible holonomy groups for the Levi-Civita connection are the following: the unitary group, the special unitary group, spin groups, or special Lie groups for the case dimension 7 or dimension 8. And in order to compute these holonomy groups, we have the theorem of Ambrose-Singer that says that we can compute the Lie algebra of the holonomy group using the curvature endomorphisms and all the derivative, the covariance derivative of these curvature endomorphisms. Okay, with all these ingredients, now other question is the following. Okay, I have a complex manifold with a Hermitian structure. There exists any linear connection that preserves this particular structure and having good properties? The answer for that is yes. This connection is the bismuth connection, for which the Riemannian metric and the complex structure are parallel, and the torsion is totally skew symmetric. That means that it can be identified with a 3-form. Okay, so we want to ask about the holonomy groups of this particular connection. Okay, Fino, Parton, and Salomon prove the following theorem. Suppose that we have a Nilmanifold with an invariant Hermitian structure. Then the holonomy of this bismuth connection is contained in SUN if and only if the metric is balanced. Okay, so we have a complete study of nilmanifolds endowed with invariant Hermitian structures and also with balanced Hermitian structures. So we can compute all the holonomy groups in each case. And with Ugarte, we obtain this result. In dimension 6, the holonomy of this bismuth connection reduced to a proper subgroup of SUN if and only if the complex structure is abelian. So the Fino, Parton, and Salomon, we obtain a more restrictive result in the case of abelian structures for dimension 6. But we obtain also other results that they are just opposite to this theorem. These examples are not on nilmanifolds, but they are on solved manifold. A solved manifold is formally is the same as a nilmanifold, but in the quotient we use a solvable Lie group instead of an nilpotent group. But this small perturbation in the definition, in fact, carry out many other differences in geometry and topology of the solved manifolds. But okay, for this case, we obtain two examples of solved manifolds in dimension 6. That for one of them, the holonomy of the bismuth connection is the whole group SU3 being J abelian. We obtain another example for which the holonomy reduces to a proper subgroup, but the complex structure is not abelian. So what happened? Which is the key point for the reduction of holonomy, because these examples seems to be in contrast to this theorem. Okay, the key point is the following. With Adrian, we study unimodular Lie algebras that is a more general setting for nilpotent and solvable Lie algebras. Endowed with Hermitian structures with complex structure abelian and balanced metric. And we prove that the holonomy of the bismuth connection is reduced to the subgroup SUn minus k, where k is the dimension of the center of the Lie algebra. So the key point of the reduction to a proper subgroup of the Lie algebra in the case of abelian structure is the dimension of the algebra. Okay, but in a later paper, also with Adrian, we have proved that this reduction does not hold if we remove the presence of a balance metric. In fact, on solvable Lie algebras and Weismann Hermitian structure, the holonomy of the bismuth connection does not belong to the special unitary group. So, putting all things together, we conjecture that the result of Fino-Parton and Salomon could be extended to the solvable case, in the sense that the reduction of the holonomy of the bismuth connection is this reduction is in a subgroup of SUN if and only if the metric is balanced. Okay, so we have obtained some applications for small dimensions in Nilmanifolds, complex dimension 2 and 3, real dimensions 4 and 6. So let us move to complex dimension 4. Observe that in these cases, in these small cases, we only have a finite numbers of Nilmanifolds. In dimension, in higher dimension, in dimension real dimension 8, we have obtained the following results. We obtain new metrics that does not exist in lower dimensions. And we have obtained, and this is the important point, infinite families of manifolds satisfying certain properties. Okay? And moreover, we have obtained a complete classification of nilpotent Lie algebras of one-dimensional center that admit complex structures. Okay, which are the problems in this dimension, in this big dimension? So first of all, does not exist a complete classification of nilpotent real algebras in dimension greater or equal than 8. However, there exist some obstructions to the existence of complex structures on nilpotent Lie algebra. So, for instance, if the complex structure is filiform or quasi-filiform, then does not exist complex structures, and also the nilpotent step should be bounded. Well, with Adela Latorre and Luis Ugarte, we have obtained a constructive method in order to obtain any pair of nilpotent Lie algebra and complex structure, and we have developed this method in the dimension 8 for the particular case of Lie algebras of whose center has a dimension equal to 1. Okay. What is the point? Well, we have an nilpotent Lie algebra. That means that there exists the ascending central series. The problem is that this series should be not adapted to the complex structure. I mean, these ideals J invariant. So Cordero, Fernandez, Gray, and Ugarte define a series which is adapted to the complex structure, and then define the complex structure satisfies certain properties according to this compatible series. So in particular, what we are interested in is in these particular structures for which this series never exists, because all the elements of this series are equal to 0. So they are these complex structures has non-J invariant ideals. Okay, these particular complex structures imposes several restrictions over the Lie algebra. So, for instance, and this is the key point, the dimension of the center of the algebra is bounded in this way. So, the dimension of the center should be greater or equal than 1, but less or equal than n minus 3. So if n is equal to 4, then the dimension of the algebra, the center of the algebra, is equal to 1. And the nilpotency step is bigger or equal to 3. Okay, so in this particular case, we focus our attention, and these are the complex structure in dimension 8. Here, all these parameters should satisfy the relations that assure that the Jacobi identity is fulfilled. Well, here observe that different values of the parameters can give the same pair JG, can produce the same Lie algebra but different complex structures, and can appear different Lie algebras. So okay, so now we can give particular values of these parameters in order to obtain several examples. So, for instance, here, I'm going to be a little more quick. So here, for instance, this family of complex structures appear giving certain values of the parameters. Okay, we can observe that if A is different to A prime, these complex structures are not isomorphic. But what happens? Perhaps it's the complex structure that is not the same. Perhaps it's the underlying Lie algebra which is different. So a more deeply study should be done, and this is a study that should be done at the real point of view. So okay, we define a real basis in this way. So we obtain complex. We obtain structure equations for a real nilpotent Lie algebra depending on this parameter A. Here we can say we can prove that we can take this parameter A to be positive, because in other way there exists an isomorphisms between algebras. And if we choose two different positive numbers, then the real Lie algebras, the real nilpotent Lie algebras are not isomorphic. Well, so in this case we obtain an infinite family of nilmanifolds, and moreover all of them admits balance metrics, and also these Gudusson metrics for all 1, 2, and 3 types of Gudusson metrics. Remember that this particular matrix does not appear in dimension 6. Okay, just to finish. Sorry. I wanted to say that we are able to classify all these complex parameters that I have shown in slides before, and all these complex structures can be codified in these small structure equations, where here appears the value of the parameters up to equivalence. And moreover, we are able to classify all the nilpotent Lie algebras underlying these complex structures. And this is the classification result of a real point of view. It is important to say that here there exists an infinite family of nilmanifolds, satisfying that all of them are non-diffeomorphic, and all of them satisfy the condition to have balanced Hermitian structures. And that's all. Thank you very much for your attention, and I'm sorry for my delay in the exposition.
Okay, thank you very much, Raquel, for your talk. Okay, then, are there any questions or remarks for Raquel? Well, let me ask you something. You said that balanced and strongly Gaussian were equivalent, but that happens in dimension 6. That's
not really equivalent. So in nilmanifolds in dimension 6, what happened is the following: if a complex structure admit a strongly Gaussian metric, if a complex structure admits a strongly Gaussian metric, then also admits a balance metric. It's not that the metric is strongly Gaussian and balanced. So the same structure admits the two types of metrics.
Okay, I see.
This is the point.
And that happens also for these families in dimension 8, or no?
No.
No.
No, it does not.
Okay.
It does not occur. In fact, this is a special type of these abelian structures in dimension 6.
It's only
in
for
dimension 8 is only for
abelian
only
complex
for
structure.
Yeah, right.
Okay, okay, good. And in the last family, in dimension 8, so you classify in the list there is an infinite family of Lie algebras admitting complex structures and center of dimension 1. Okay.
Mm-hmm. Yeah.
Okay. Okay. Yes.
So here is this family here that it depends on 2 parameters, and is these particular values that all of them are non-isomorphic, all of them admit complex structures, and all of them admits a balance metric.
And the complex structures here are all strongly non-nilpotent.
Yeah. All this study is for this particular type of structures. In fact, all these algebras has a dimension of the center equal 1. Okay. This is equivalent to the complex structure to be strongly non-nilpotent. In dimension 8, this is equivalent.
So they do not admit any complex structure of the other types? No. Not non-nilpotent?
No.
Okay, good. Okay. Great. That's very nice to know. Well, thank you. And are there any other questions or remarks for Raquel? No? Okay, let's thank Raquel again. Thank you for a very nice